Welcome to EDU World Space.
So to start solving this question, let's take a look at a crucial equation that'll help us throughout most of this equation. So the potential difference between the surface and a distance outside the cylinder from the central axis can be given by this equation. So the potential is equal to lambda over 2 pi times the permittivity of free space times the ln of the distance r over the radius capital R. So now to execute the potential difference depends only on R and not the direction. So it only depends on the distance but not the direction. So therefore all points of the same value of R will have the same potential. So they will be equipotential surfaces, and these equipotential surfaces are cylinder coaxial with the given cylinder. So we're given that the radius of the cylinder is equal to 2 centimeters, and the linear charge density, which is lambda, is equal to 1.5 nanocoulombs. So if you just plug this into this equation and solve for r, solve for the distance. So let's actually do that first and solve and isolate for the variable r. So if you do that, you're going to need to bring all of this to the other side first. So let me go ahead and erase this. So multiply 2 pi times the permittivity times the potential and divide by the lambda. So we're going to get that ln r over capital R is equal to the potential difference times 2 pi times the permittivity over lambda. Now, if you were to just isolate for R, all you need to do is make both these the coefficients of E to get rid of the ln. So now we're going to have R over R, and we could actually take this one step further and multiply the capital R to the other side. So if you do that, you're just going to get R times E, and this whole expression up here is just going to be the coefficient of E. I mean the exponent of E. So this is an E, just in case you didn't realize there. So it's R times E to the power of potential difference times 2 times pi times the permittivity over lambda. And this is just equal to the distance small r. And now if you just plug in all the values for potential and the permittivity and lambda, which we all know, we're going to find out that the radius or the distance is equal to, or let's actually go ahead and plug them in just for clarity. So it's 2. So we're given that the radius of the cylinder is 2 times 10 to the negative 2, just to put it into SI units, times E to the power of 2 pi times 8.85 times 10 to the negative 12. And this is just Coulomb squared over Newton meter squared times 10 volts over lambda, which is just 1.5 times 10 to the negative 9 coulombs per meter. So now if you compute this in our calculator, we're going to get that the radius is equal to 2.9 centimeters. And similarly, if we solve for the other voltages, for the several other voltages that we're given by using the same process. So this is using voltage 10. So let's make that clear. V equals 10 for this one. V is equal to 10. So now I don't think I need to go ahead and write this, since the only thing we're changing here is the voltage. So if you just substitute the different voltages, we're going to get that the radius in this case is 4.2 centimeters. And now for voltage 30, V is equal to 30. The radius is going to be 6.08 centimeters. And now for the final part. So this is A, this is B, and this is C. So to solve for the radii, all we need to do is subtract the initial from the subtract the final from the initial. So the change in radius 1 is equal to 2.9 minus 2, which is just 0.9 centimeters. And then for radius 2 is equal to 4.2 minus 2.9, which is equal to 1.3 centimeters. And finally, for the change in radius for the third one, which is 6.08 minus 4.2, which is just equal to 1.88 centimeters. So now, as you can see, the change in radius increases, so the surfaces get farther apart. This is different from a sheet of charge where all the surfaces are on an equally spaced plane. And that's it for this question. Thank you for listening, and see you.